Thank you. Thank you, Greg. It's a pleasure to be here virtually in the workshop. And yeah, I mean, I think all these areas coming together is very exciting for me. You know, for me, coming from the perspective of laying down algorithmic foundations for AI and asking how we can solve some of the hardest scientific problems has been a very exciting, but also a journey where I've learned so much. The domain experts, what they have to offer in terms of all the methods that have been developed over decades. The domain knowledge and the constraints, how to incorporate that into machine learning. And more importantly, for these methods to be ultimately incorporated in real world applications, we would need to design AI that can extrapolate, not just interpolate to a distribution similar to the training data, but make entirely new discoveries, right? Like what we call zero-shot generalization, be able to generalize to new instances that are never seen before and that are out of distribution. I think these are aspects that also challenge us to design better AI, right? Ultimately, if we want to think about any form of highly generalizable AI, that would also be very impactful for the sciences. And so that's where I see a virtuous feedback loop here, that we AI scientists can contribute to all different domains, but also learn from those domains, the challenges, the constraints, and how to incorporate that to design better AI. And that's been my journey over the last few years, and both at Caltech and at NVIDIA. At Caltech, I co-founded the AI4Science with Isong to really build AI into all scientific applications across campus. How do we create this fabric of collaboration and come up with ways to scale up these methods to large-scale data sets, to real-world problems? And if the data is not available, how do we incorporate domain constraints to have meaningful results with machine learning? And on the NVIDIA side, as you will see in this presentation, the HPC aspect of it is something that NVIDIA has had now more than decades of experience in terms of building supercomputers and serving the scientific community. And so now, how do we bring that to the modern age and combine both AI and HPC together? What kind of computations at scale can we enable with high efficiency, and what kind of scientific problems can we solve? And that's where both my connections to NVIDIA and Caltech have been very helpful in informing these problems and coming up with good engineered solutions for them. So anyway, that's a very quick overview of my intentions here today. And yeah, let's get started. So to me, AI is perhaps the most powerful technological force we've seen in our lifetimes. We've seen the model complexity just explode, right? From the time AlexNet was created to now GPT-3 and beyond. You see this now new form of Moore's law. It's doubling every 2 months if you think about the largest models that are being constructed. And that is really exciting in terms of, HPC community, right, was traditionally focused on scale, and now AI is the new HPC in the sense of the largest models are getting built with AI foundations and ultimately integrating HPC and AI together. And now we are delving into harder problems, whether it's drug discovery, which I will talk about later here, but also like all kinds of embodied AI, right? Like building intelligence into robotics is highly non-trivial because of interactions with the real world, maintaining safety, stability constraints while being agile and dynamic and learning all kinds of new environmental conditions. So lots of hard challenges, but also ways to incorporate that into our AI frameworks has been very exciting. And so given this, I just want to quickly remind everyone that what has resulted in this AI revolution is really the trinity of data, algorithms, and compute infrastructure coming together, right? So, and now when we are going to the sciences, we also want to ask what kinds of data is available. And there are some scenarios where lots of data is available. For instance, when you think about astronomy, right? We are barely able to manage all the data that is collected in the satellites. Most of it is discarded even before it reaches the Earth. On the other hand, there are settings like protein engineering where the lab experiments are extremely limited. So, we need to be able to adapt to both very large data sets to very small data sets. And then there are domains where we know lots of physical constraints. I'll talk about partial differential equations where, if your entire goal is to only simulate the PDE, you know the constraints exactly, right? But then there are complex systems like, any biological mechanism where you cannot have a precise model. So then do you impose any kind of imperfect prior knowledge, or is it better to be fully data driven? I think that facet of it, right, again, it's not one size fits all. We need to be able to incorporate all kinds of different constraints. And sometimes when there are none, how to be informed purely by data, especially when the data sets are small. I think this aspect is important to think about. The compute aspect is also getting to be more important. Traditionally, like I mentioned, HPC has been very high precision computing. 64-bit is the standard, but with AI algorithms, we are going to extremely low precision, even as little as in one of our latest papers, we showed you can handle with just 5 bits and get the same accuracy on ImageNet and other big data sets as the full precision models. So if that is the case in standard AI benchmarks, what would the implications be for the sciences? Do we still need very high precision in each part of the pipeline, or can we afford to do low precision? And if it's AI is involved, can we then adapt to low precision frameworks and hence be a lot more efficient? And that's, I think, a big equation that is forming now. And we've seen a lot of good evidence that we can even handle hard scientific problems in low precision with the use of AI. And also the other aspect is on the edge. When we are building now robotics, we are building sensors, we need to ultimately miniaturize it to small devices, expose it to all kinds of environmental conditions, limited battery power. So we can no longer afford to just expect that there will be the cloud, right? So in those kind of applications, how do we design better algorithms? So that's where I think there is just a huge renaissance of developing new AI algorithms because the standard paradigm of supervised learning, what made ImageNet challenge successful was pretty standard supervised learning, right? But going beyond now to unsupervised learning, causal discovery, zero-shot generalization, they require new algorithmic frameworks. And so that's why it's, I always start with this motivating slide of Trinity, because we cannot design one in isolation, right? Where if we are questioning about what algorithm to use, we need to certainly ask what kind of data do we have and what kind of compute infrastructure do we run this on? And all this has to be co-designed. Ultimately, we can envision, right, co-designing all these three facets together for specialized applications to get the best efficiency. And that is indeed the connection also with HPC, right? Like I mentioned, there has been continuous improvement in terms of frameworks getting better, but the biggest improvement is really coming from not running the traditional HPC with, say, 64-bit precision, but AI computations in much lower precision. And having this available means we can run, like, say, the largest molecular dynamic simulation like that was done last year but use AI to accelerate that and be able to make use of the flops efficiently. And I think that's an exciting future in terms of the larger scale. How can we use AI in meaningful ways? And indeed, the recently announced fastest supercomputer will be ALPS with 20 exaflops of AI, right? So it's mind-boggling in terms of the scale we now have compared to just a few years ago. And it's really the use of AI that can now enhance the flops by a huge amount compared to just the traditional HPC. And also, thinking about hardware optimizations, having GPU and CPU being tightly optimized together can give us a lot of benefits in terms of efficiency. So this is on the computational side. Now, if you think about what kinds of challenges are compelling to solve with such supercomputers, right? So indeed, to me, and probably to many of you, the climate change is the challenge of our times, right? And especially over the last year with the pandemic, with all the fires, in California, floods in Texas, everything we've seen, the extreme weather events seem to be accelerating, and we seem to be at the precipice of big climatic changes. And so I think it should have been yesterday when we were already thinking of strong interventions, but now hopefully the global community is further energized to, go through having availability of these good models and then designing interventions. And for that, predicting uncertainty is also important. And what makes this predictions very challenging is the highly multi-scale nature, right? For instance, the Climate project here at Caltech looks at multi-scale models. So you have a scale for the clouds. And in fact, there is a further micro scale or a microphysics for precisely modeling precipitation. And ultimately, you want to map it to global measurements taken by the satellites. So all these aspects of first simulating at every scale and then mapping it to the coarser scales makes it expensive and challenging. And to do this at planet scale is a huge feat. And ultimately also giving uncertainty measurements, right? Because you don't just want a deterministic prediction, right? That's meaningless. You have to give calibrated uncertainties. And the Climate project here at Caltech has been spearheading all these aspects, and where we feel that AI, one of the places AI can play a role is, for instance, in being able to accelerate solutions to partial differential equations, right? And that was just one example where that is applicable, but so many others. In fact, it's no exaggeration when Steve Strogatz calls the differential equations the most powerful tool humanity has ever created. So, everything from fluid turbulence to material design is incorporated as partial differential equations. And the equations themselves are very usually succinct and easy to express. But what makes it highly challenging to solve is that all these complex equations do not have a closed form analytical solution, right? So you have to do numerical brute force computations and do that also in multi-scale. Like you have to go to the finest scale. So you cannot afford to just take big discretizations, because then you lose information, the high frequency information in those phenomena. And so that's what makes it challenging to do this in traditional methods. And the other aspect is, with these traditional methods, you're redoing all the computations, right? So even if you slightly change your parameter or your initial condition, you have to redo everything from scratch. Whereas the hope is, with machine learning, you learn the underlying structure of the solutions, and hopefully you can generalize to now new conditions, new points in a meaningful way. And so that was our goal, to design machine learning methods that can be way faster compared to traditional methods, but also be as accurate and have guarantees of being able to get good solutions, at least in some scenarios. And that was this interdisciplinary project we started on neural operator. And at Purdue, you have now Kamyar. He's been such a pleasure to work together, first as a student and then as a postdoc with me. And I'm really happy to see him be at Purdue and have a great time there. So, given his initiative and having Andrew Stewart from Applied Math and Kaushik Bhattacharya from Material Sciences and the students and postdocs together created this interdisciplinary initiative. And I think that I want to quickly emphasize that that was critical to success of this project, because having all these perspectives, having the wealth of knowledge from all of the methods that have been developed over the decades, thinking about these multipole methods or thinking about iterative solvers, right? So all these gave us inspiration to design neural networks, but have these kinds of structures that are informed by traditional methods. And I think that has been critical for us to get good, successful outcomes. Yeah, so in terms of framing this problem, the way we wanted to frame it is one that can, right, in principle, you should be able to treat it as any traditional solver, right? You should be able to give different initial and boundary conditions. Let's say you design a solver for a parametric family like Navier-Stokes for fluid turbulence, and then you give some initial and boundary conditions, you should be able to get the solution. And in order to be able to do that, you need to first train your neural network by giving a whole set of initial and boundary conditions and the corresponding solutions. So this is a data-driven method. And indeed, you may ask, in some situations, I don't have data, right? Because it's so complicated that the traditional solver would be too difficult. So later on, I'm going to talk about using only the physical constraints for training. But for now, let's assume the setting you have such training data. So you have the availability of a whole set of initial and boundary conditions and the corresponding solutions. So if this is the case, it seems trivial, right? I can just put this into a standard neural network, maybe convolutional neural network, or even fully connected network, and hope for the best. Why is this not just that trivial? So the reason it's not trivial is what we want in our solvers is really a function-to-function mapping, right? So ultimately, you're mapping initial and boundary conditions over all arbitrary discretizations or even continuous sets to the corresponding outputs, which are the solutions at those points. And whereas traditionally, what we have is really just fixed-sized inputs and outputs, right? So the vocabulary is fixed in language. In image, the resolution is fixed. You assume images of a particular resolution. But this won't work for the case of PDEs, because as I said, you should have the freedom to give any kind of discretization, right? You may, in some application, require your solver to just give you answers in this coarse discretization. In a different downstream task, you need your solution to be available at all kinds of fine discretizations. And even the meshes, you could have all kinds of designs of meshes. So how do we, in principle, formulate a neural network framework that can incorporate all these different scenarios? So you should be able to have one that is invariant to the input being any discretization or any grid. And so that's what led us to thinking of this as an operator learning, because now we are learning an operator that maps, infinite dimensional spaces, right? That's a mapping between infinite dimensional spaces. And so that makes it fundamentally different and a generalization of our standard neural networks. So in order to go about this endeavor, we go back to the standard neural network, and then we want to ask, how do we extend this from like finite dimensional inputs and outputs to infinite dimensional spaces. And to do that, right, the main principle is you have certain linear operations and then nonlinearity. And composing this gives us universal approximator, right? Because if you just had linear operation, that is not expressive, right? That's just a linear model. And that's what gives the expressive power of neural networks, is this composition with nonlinearities like ReLUs or all kinds of nonlinearities. And so the question is, when we are now extending this to infinite dimensional spaces, can we still retain this overall structure? But now this linear operation, can we replace it to handle infinite dimensional spaces? For instance, here for finite dimensional networks, it's just some form of matrix multiplication, right? So like in fully connected networks, or convolution operation, which is also linear. So there you're assuming fixed sized inputs and doing a linear operation. So now how do we extend this? And to do this, we take inspiration from linear partial differential equations. So when you have linear partial differential equations, we know the solution is in the forms of a Green's function. So this is the diffusion equation, perhaps the classical and the simplest equation, right, of heat diffusion. And there we know the form of the Green's function. And to obtain solution at any point, what you do is you do this convolution or integration over this kernel here, or the Green's function. And so that's how you can express your solution at any point. So given this knowledge, right, if we can now express this layer as this integral operator and then compose it with nonlinearity, what we get is a highly expressive network, right? In fact, we can prove that it is a universal approximator. So just as on the lines of finite dimensional neural networks, we can now prove that any continuous operator can be approximated by a two-layer neural network, or a neural operator, sorry. So, and indeed, in practice, you can have more layers depending on the compositionality you want. But this kind of shows that you can now have an expressive framework to express any general operator using this neural operator framework. But indeed, then the question is, how big will this neural operator be, right? How many parameters will this architecture have for different operators? And that certainly depends, right? So for instance, for popular families like Navier-Stokes, what we do know is that the solution operator lies in a low dimensional space. So meaning you do not need as many parameters to express this. And that's why you can get these kind of results where you can provide bounds on the size of the neural network architecture to express the solution operator of Navier-Stokes. And that's why, right, there is no magic here. I mean, if we are we are capturing operators that map between infinite dimensional spaces. But if the operators themselves are finite dimensional or low dimensional, then we can use a compact neural operator to express it. And that's where we get both the expressivity, but also compact ways to capture the operator. And note that even though the number of parameters will be small, this neural operator will still be resolution and grid invariant, right? So that's the power it has. So you can compactly express the entire solution operator rather than capturing only the solution at a specific discretization or grid. And so now the next question is, how do we actually solve this, right? Because the whole aspect was, we just conceptually said, if you can solve this continuous integral, right, this integral operator, so you somehow learn this kernel and then solve this integration, and if you can do that in each layer here, then you get a universal approximation. But how do we now design practical architectures to solve this integration efficiently. And that's where we tried different variants, right? So natural thing is to use graphs to like nearest neighbors to capture the learning of this kernel. But what we found to be most effective in almost every equation family that we tried is the Fourier transform. And indeed, right, so many traditional solvers also use the Fourier transform, like the pseudospectral solvers. And so that's can be a very important and a good inductive bias for solving this convolution or integral operators. So what we see is with the Fourier transform, just to remind you, the signal processing 101, right, this convolution in the standard domain becomes multiplication in the Fourier domain. So what you're really learning now is this weight matrix, right? So you're learning a weighting in the Fourier domain or the frequency domain of your input signal, and then doing the inverse Fourier transform. And one of the intuitions of why Fourier transform is very powerful here is the availability of this global correlations, right? If you think about just standard convolutional neural networks, the filters are small, so you can only capture local features like edges. And the receptive field over multiple layers, right, will not be that big. And also, you're kind of filtering out, so you're not able to capture the entire domain very effectively. Whereas with the Fourier transform, it's global, right? You're capturing global correlations, both spatiotemporal, correlations. And that's really important in domains like fluid turbulence, because we know there is global dependency. And so that's one of the reasons, people have earlier tried like convolutional neural networks or UNets, and it hasn't been very effective if you want to try and solve the equations from scratch. And so that's kind of the overview here with the Fourier transform, right? So what you're doing is learning this weight matrix that mixes the different Fourier modes here, but we only filter out the low frequency mode. So we only retain a small number of modes, like say 20 modes. But this is okay because we are now composing it with nonlinearity over several layers. So even by retaining only low frequency modes in each layer, because we have the nonlinearity in the end, we can capture all the high frequency components as well. And to make this practical, we also add a bias term, because sometimes the non-periodic boundary and other conditions could be hard to capture with just the Fourier transform. So having this kind of additional path can be helpful here. And yeah, and that's it, right? That was a simple framework, just to kind of remind you the overall framework before I show these results. What we had is multiple layers of this Fourier transform, right? And learning the weight matrix over that and filtering out the low frequency components, and then having nonlinearity like ReLUs and composing it over several layers. And there's one detail I left out, because we can also first lift our inputs to, say, a higher dimensional space, right? Have more channels, and also project it back to the solution space in the end. And that's, we see to be effective because the lifting kind of makes it easier to learn the solution here. Yeah, so what is the outcome? We've been very excited to see that we are able to solve the Navier-Stokes equation here. And, that too, you can see this pretty turbulent regime here. And the thing that to me is so exciting is we were able to train on extremely low resolution data, right? So this is the this is the spatial, and this is the temporal resolution. And then at test time, we can directly evaluate it for higher resolution outputs. So this is what we call zero-shot super resolution, because we do not need access to high resolution data, right, at training time. So it makes training also extremely cheap and fast. And then we are able to adapt without any additional training at test time for any arbitrary resolution, including much higher resolutions. And I think that's the power of this neural operator. And what we see is also that this method, right, when you train and test on the same resolution is also better than the other methods. I mean, this is just kind of a quick comparison with the other machine learning methods, right? Because the others are not capable of this kind of zero-shot super resolution. You know, you cannot train on one resolution and generalize on other. But just a quick comparison to show even there we are doing better. So we do well at the same resolution, but also generalize to different resolutions with very low errors. And as I said, the important thing is to be able to capture the frequency spectrum, right? And we know there are all these high frequency content in these turbulent fluid flows. And we see that we are able to capture well, especially if we also train with derivative losses, which the Sobolev norm captures. And I think that helps the recovery. And if you recall, the aspect that makes it tractable to capture this high frequency is, you know, at each step, we are retaining only low frequency modes for stability and regularization, but ultimately with nonlinearity, we are able to, you know, have transformations and capture also the high frequency content. And with this, it's now natural to use this as a module in all kinds of problems like inverse problems. I mean, here we did the Bayesian inverse, right, with MCMC and forward sampling to do an apples to apples comparison in terms of speed up. But you can also think about solving the inverse problems directly by differentiating through the neural operator and you know, converging to an initial condition. So these aspects, I think, will be very effective because in so many applications, we have inverse problems, right? Because what you have is an evolved map, you know, something that has spatio-temporally evolved, for instance, and then you want to go back and recover the initial conditions. And so this can be very effective in speeding up those problems. And now, you know, once this tool is available, we've tried it on a variety of domains. So I'll give you quickly some outcomes of this, you know, effort here. And so plasticity is a problem that, you know, Kaushik Bhattacharya and Burigade have worked extensively on. I won't get into the details, but it is a multi-scale problem. And so you have solvers at different scales. And what we did was, instead of throwing out the entire traditional framework, right, which I think for neural operator would be very hard to solve in the first go, and especially, you know, in a single GPU, we cannot fit such a large model, right? So instead, what we did was to only replace the solution operator at the fine scale and keep the traditional solver in the core scale. And even with doing that, we get very high accuracy while being 5 orders of magnitude faster. And in this case, we use simple PCA basis, and that was already very powerful. And so this shows, you know, the ability to speed up very effectively many of the traditional simulation packages and have easy ways to plug in our method. So another exciting application is ultrasound, and here, you know, we want to like capture both the wavefront and diffraction, you know, in order to kind of capture the, you know, properties of human organs, right, whether there is a tumor or not. And so we've seen good promise here in being able to capture that with neural operators. So this is an exciting problem in terms of, you know, I talked about climate change in the beginning, right? So one intervention mechanism that has been proposed is whether we can store carbon dioxide underground, right? Capture and store. And this is a complex multi-phase flow problem. And, you know, we've found very promising results in terms of having a combination of unit and FNO architecture, right, that kind of captures both the local and the global phenomenon very in an expressive way. We'll soon release this paper, and I think we got 4 orders of magnitude speed up here. And so as you can see in these range of applications, we see lots of benefits in terms of using this neural operator architecture and still being able to retain the fidelity of traditional solvers. Yeah, so early on I mentioned that what I covered so far has been this data-driven approach, right? So we have even ignored the equation constraint. We've just said, give me the training data that maps different initial and boundary conditions to solutions, and we'll train the neural operator. But instead, you may also want to incorporate the equations themselves, right? So how do we capture both the constraints in the equations and data together? And in some cases, maybe there is no data available because it's too expensive for the traditional solver to give us this training data. So in that case, can we purely just use the equations and at test time, so that's one aspect during training, right? So the other aspect is at test time. So far, we don't have a formal guarantee that this trained neural operator will be able to solve every instance of the problem. But that's where, if we can further optimize the test time. So we have a trained neural operator. Now at test time, we look at a specific equation and then we say, for this initial and boundary condition and this parameters, let us see what the pre-trained model does. And we can further fine tune on the equation laws, right, to obtain the best possible fidelity or accuracy of our solution. And so this kind of just shows that we can further enhance and give now guarantees, right? Because you can then evaluate if the equations are satisfied or not. So you can have then a confidence in terms of how good is this solution. And so that's what the benefits we obtain. We call this PINO because we have both the physics informed and we have the neural operator together. Whereas the standard physics informed neural network is just doing this on a single instance of the problem, right? So it's only doing this at test time, meaning just on a single problem instance, solve it directly. Whereas what we are saying is, if we are now pre-training on a family of PDEs, right, with different initial and boundary conditions, even if we don't have training data, that pre-training will help us capture the structure of solution operator better. And at test time, that fine-tuning will further ensure that we get ultimately a good solution. And so we do see benefits here, both in terms of being able to converge much faster with pre-training, and for more harder problems like a longer time interval, in fact, be able to get to a better solution, a better error compared to just training from scratch, which really means on that problem instance, you're just doing the pin. That is not as effective compared to also having the pre-training. And so we see here very promising solutions, in terms of getting good errors and also being able to generalize from one Reynolds number to another. So having this combination of physical constraints along with data-driven approaches will be very effective in many of the real-world scenarios, because you usually have a combination of both of them. And in some scenarios, if you have no data but only equations, we can also handle that. And vice versa, you don't have any equations, you only have data. So you don't want to, limit it to one set of parametric equations. That is also okay, right? So this is a very flexible framework. Yeah, so far what I showed was the framework of trying to predict, right, a trajectory, whether it's in terms of velocity or vorticity. You see here, our goal has always been to spatiotemporally predict the solution, right, over a period of time. But ultimately, we do not expect this to keep tracking the trajectory forever, right? Because what we have in these systems is a chaotic system, right? So there's a lot of classical theory that's known about this. It's called the butterfly effect as well, right? So you make small changes here, the trajectory completely diverges, right? So there's no hope of predicting the exact trajectory over a long time period. So if that is the case, what can we hope to predict? And that's where in this latest work, what we said was in most of these systems that are of popular interest, we can expect that there are attractors, right? In some cases that is formally proved, in other cases there are strong conjectures about attractors, whether it's a single attractor or a finite set of attractors. So given this is known, the idea is, over a long period of time, our predicted trajectory will ultimately diverge from the ground truth. But if we can preserve those statistical properties, right? If we can preserve the same orbits or attractors, then we have captured everything about the system, right? Then we can claim we can accurately simulate the system. And that's the best thing we can hope for in chaotic systems. And this, is very different from traditional temporal predictions. If you think about recurrent neural networks or LSTMs, the goal is always to try and fit the entire trajectory, right? It could be a very long trajectory. You try hard to fit and drive down the error of prediction. But we know this inevitably will fail. You'll have your recurrent neural network having exploding or collapsing gradients, because this is inherently unpredictable. So you should not be training this on long time periods. And so that's a basic philosophical observation we made here, that you should really be only trying to train on local or small time step transitions, right? So what we call a Markov operator. So it's only like looking at the transition of the current time period to the next. By the way, all these dynamical systems that, like the KS equation, right, or this Navier-Stokes are all Markov systems, right? They are fully observed Markov systems. So we know if that is the case, the future evolution is only based on the transition operator or Markov operator in a small time step. If you have that, you can just integrate it over the time, and that's how you obtain your long-term behavior. So given that is the case, our goal is then to learn the operator, this transition operator, using neural operator framework. And then at test time, all we do is just compose it many times, right? So we are never training on a long trajectory. We only train to capture local evolution, right, on a small time step. And then we just zero shot compose it to give us predictions over a long time, and that'll give us statistical properties about attractors and many other properties. And so what we see here is fascinating, right? As I said, over a long time period, it is indeed impossible to capture the entire trajectory. But an interesting observation is that, like standard frameworks like LSTM or GRU, all these that train on a longer time step, right, actually capture the trajectory worse compared to our neural operator that is only trained on small time steps and then just composed directly to get the predictions over the longer time period. So which is fascinating, right? Because this is not the loss on which the neural operator is trained, but still, because it's effectively able to capture this local evolution, it can compose it in a good way and still try to keep track of the trajectory better than these models where you're trying to train on a longer trajectory, but because it's hard to learn, it fails to generalize well and track these trajectories well. And so what we see then is, we then looked at for these local, right, operators, can we, for capturing the local evolution, can we use other frameworks like UNet in addition to the neural operator? And what we see is we're able to capture the spectrum better compared to the units. And, so I think the spectrum is the most obvious one. And that's kind of intuitive, right? We are much better at capturing high frequency content because the neural operator is resolution invariant. And so that property we can benefit from in also capturing the statistical invariant properties or the invariant statistics of all these chaotic systems. And what we see is, also just kind of an intuitive plot here that, this we can capture the attractors well, because the idea here is this, right, lower dissipation, like this is kind of the movement along the attractor, right? That's kind of the idea. So we are able to capture the phenomenon of the underlying chaotic system well by using the neural operator to capture the Markovian evolution. Yeah, so, so I think those are some of the main aspects I wanted to cover. And just a quick comment here that, there's a close connection with transformers, which people may not realize. I won't get into the details here, but, this attention mechanism is very expensive in transformers, and you can replace the kernel with Fourier transform and get similar architectures to these neural operators. And in fact, we can prove that in the general framework of neural operator, transformer is a special case. And so we can get kind of, these other architectures that are very similar to the neural operator, where there's been promise also on standard image benchmarks. So I think there are some nice connections. So this is not just limited to PDEs, but a much more general framework. Just a quick comment on, at NVIDIA, we have SimNet as a way to build these methods at scale. At the moment, we have the PIN implementation, and we are adding the neural operators into it, and being able to, do all kinds of aspects such as the forward inverse and the data assimilation simulations at scale, and being able to, have support for, say, mixed precision, right, multi-GPU. So really enabling you to tackle practical problems at scale here. Yeah, so really the takeaway I have here is this notion of learning the operator is a generalization of standard neural networks from mapping between finite dimensional spaces to now infinite dimensional spaces. And by building a foundation of using integral operators, right, this convolution with a kernel as the linear operator, and then composing with nonlinearity helps us come up with a universal approximation framework for any operator. But we also see it's very practical because we can use the Fourier transform. It's a great inductive bias for many of these families. It can capture the global correlations well, and at the same time be much faster than traditional methods. So I hope I gave you an overview and also so many exciting applications. Really looking forward to your thoughts and any questions you might have.
Great, well, thanks very much. We might have time for a quick question or two. Anyone have a question?